Hi guys, in the second part I want to go a bit more into the details how the ULM assembler is generating machine code from your source file and how the symbol table and this fixup table is used for doing that. I will first use an example to show you how this code generation gets done, an example where you already know how it should look like in the end because you were writing first the Hello World program directly in machine code. And after you did that, I showed you more features of the ULM generator that you also can specify in your instruction set some assembly notation for every instruction. And then the ULM generator also generates an ULM assembler. And together with this ULM assembler and your assembly notation, you could rewrite your Hello World program like that, where every instruction is now expressed with this assembly notation, and this .string directive is used to generate the data for the string, this zero-terminated string. And with that, it was more convenient to write a program like that because you didn't have to memorize anymore all these opcodes and instruction formats, but it still was equivalent after the assembler generated code to what you did before by yourself. Still kind of annoying or inconvenient was that you had to compute, for example, addresses manually. For example, this address of the hello world string, so that you could store it in a register. And if you would add some instructions to your program, you would have to recompute these addresses because they would change. You also had to compute manually jump offsets, how many instructions you want to jump forward or backward. And you also had to memorize that in this example, register 1 was always used to store an address of a character, and register 2 for storing actually the character itself after fetching it from memory. And to overcome all these limitations, you could use the labels for marking instructions or data, and this equivalent directives for giving numbers symbol representation. And in the end, we had basically this Hello World program with one modification, which makes it more interesting to show you how this code generation gets done in general. These equivalent directives are now at the end of the assembler program. In order to understand how the assembler is generating code for you, you have to know how the assembler is doing the bookkeeping for you, what you before had to do by yourself. And in order to understand this bookkeeping part, you have to know that every expression in your code not just has a value, but also a type, like in C. But compared to C, this type system is much simpler. Here we basically just have 3 types. If an expression in the end evaluates into a plain integer, it has an absolute type. If it in the end evaluates into an address, it has a so-called relocatable type. And because addresses can either be in the text, data, or BSS segment, we actually have here 3 subtypes. Why this is called a relocatable type will become more clear when we talk about linkers. Now here we also have this unresolved type. And you already saw that using a symbol that was not previously defined by a label or by a .eq directive is not considered as an error in assembly. This symbol then just has this type unresolved. And maybe later this type will change after the assembler reads a label definition or a EQ directive, or it stays unresolved. The assembler is using a symbol table for evaluating expressions and also doing one part of the bookkeeping job. And you will see in the example that, for example, label definitions or EQ directives generate new entries in the symbol table with a particular type and particular value. You will also see that if an expression contains a symbol that was not defined so far, this also just generates a new entry with initial type unresolved and initial value 0. In the example, you will also see that in some cases, the assembler is generating incomplete instructions or instructions that need to be fixed later or can be fixed later. For example, jump instructions seen by the assembler together with a label that hasn't been defined yet. It means that this jump instruction has an operand with an unresolved expression and initial value 0. From that, it generates code, and this code can be fixed later if this label gets defined later. Now, in order to fix it later, 2 things need to be stored in a fixup table. where to fix something and how to fix it. For now, this will be sufficient for this example to know that this two pieces of information are stored in this table. You see the details are a bit more complicated. You will also see that together with the linker, this Fixup table is also needed, and a bit more than just unresolved expressions will lead to entries in this table. So we will talk about this anyway in more detail again. What is still missing for the bookkeeping part is keeping track of bytes generated for the segments, and for that the ULM assembler is using virtual memories for the text data and BSS segment. And here you see that initially the virtual memories are empty, the tables are empty, and this text segment is active. That means by default data gets generated for the text segment. Now with this setting, I will show you how this Hello World program gets processed in 2 passes and how then this assembler output gets generated. So this is the example where I want to show you how the ULM assembler is generating code. And now I have a spacing problem because I also need to show you this internals of the ULM assembler, this tables and this virtual memories. But because the ULM assembler is just processing this file line by line, you actually just have to see from this complete source file the current line that is processed. And you see that the assembler begins with the first line of the file. And in this case, we have a directive for activating the text segment so that generated code gets assembled there. But because the text segment is anyway the default segment, this has no visual effect. So let's continue with the second line. And here we do have an assembly notation for instruction. So this gets passed, and then expressions here need to be evaluated. And we actually do have 2 expressions because symbols are also kind of expressions. And that means the assembler needs to look up the value of message in the symbol table. It's not there, so it will create a new entry here with type unresolved and initial value 0. And the same will happen for this expression here. So we will have 2 new entries with initial value 0. Then code gets generated for this. The assembler will look up in your instruction set what is the opcode for this assembly notation. And the opcode is hex 08. And from looking up this instruction, it also knows, of course, the instruction format, that it has 2 fields and how to initialize these fields with values from these expressions. And because currently these values are 0, it will generate 0 bits here, a 0-bit pattern. And now you see code actually was generated. You also see that the alignment, the requirement for the alignment changed to 4 because instructions need to be aligned to 4. And that means if later this text segment gets replaced to some different location, this information is available. You will see it in the executable. But you also see now that these fields later need to be fixed because, of course, this symbols message and header will later be defined somewhere. And so we need these entries in a Fixup table to allow that. And here you see that this first entry specifies that these 2 bytes here, 16 bits, need to be fixed later with the value from the expression MSG. And also this byte later can be fixed with the value of header. And that's it for encoding the first instruction and generating code for it. The next instruction is the label. This will always generate a new entry in the symtab. If entry with this identifier already exists, it would be an error because you only can have unique labels. The type of the label is always a relocatable type, and its actual subtype depends on what segment is active. Because the text segment is active, this will be an address in the text segment, and the value of the label will always be the number of bytes so far generated in this active segment. So that means we will have an entry with value 4. And that's it. We do not have an instruction here. So the next line contains, again, an instruction, and it also contains 2 expressions. These will, again, be evaluated first. Again, this will generate a new entry in the sim tab. Adder is already in the symbol table with value 0, and this ch generates a new entry with type unresolved and initial value 0. And after that, the code gets generated for this instruction after looking up the opcode and the instruction format, and then it gets encoded. If a field is unused, it gets 0 initialized by the ULM assembler. That means we again generate 4 bytes in the text segment, and again we need to fix things later, eventually. And you will see in this case, this is actually happening. But that's it for this next instruction, and so this will continue like that. Here again we have in this instruction expression, which again needs to be evaluated. This will not generate a new entry because we already have a symbol for that in the symbol table. And so we just look up the instruction opcode and the instruction format, encode this instruction and generate code for it. And again, things need to be fixed later. So again, entries in the Fixup table. The next instruction will generate here a new entry because this hold symbol is so far not listed in the sim tab. So a new entry with type unresolved and initial value 0. Then again, lookup of the instruction opcode and instruction format. Then for encoding here, the ULM assembler will right shift the value of the expression by 2. Here you do not see any effect because the value is 0. So you will see that it generates here the opcode followed by 3 0 bytes. And the same pattern. The counter gets incremented, new entries in the Fixup table, and like that it continues for the next 2 instructions without a big difference. All the symbols for the expressions are already in the symbol table. So let's just proceed a bit more quickly. You see again, counter gets incremented, new entries in the Fixup table. Next instruction, same pattern. Also, the symbols are already in the symbol table found. And this also generates just another incomplete instruction. But now the next instruction has finally an expression which is not of type unresolved. Fetch is listed here as a relocatable symbol, address in the text segment with value 4. And that means now, after looking up this instruction format and seeing that this is a jump offset field, the assembler is computing this jump offset for encoding this jump offset. And for that, it first takes the value of this symbol, of this expression. It's the address of the text segment plus 4. And from that, it will subtract its current position in the text segment, which is the address of the text segment, because that's the active segment, plus 24. So this will be subtracted from that, and this gives an absolute value with value minus 20. We want to jump back 20 bytes. For encoding that, it also divides this by 4, because we want to jump back 5 instructions. Every instruction has 4 bytes, and internally, of course, it's doing that with a right shift by 2, applied to the bit pattern. And this will be encoded as a signed integer, this minus 5, with 2's complement. And here you see that no new entries were generated in a Fixup table, so this is a finally complete instruction that doesn't need to be fixed later. In the next line, a label gets defined. In this case, this will not generate a new entry in the symbol table because we already have there a symbol hold. So far, this symbol has the type unresolved. Now it gets resolved. The type will be changed to address in a text segment to a relocatable type with value 28, the value of the counter of the active segment. Now here, the assembler might detect in some cases an error. If you use the same identifier for 2 different labels, then this identifier is found in the symbol table with a type different from absolute and unresolved, so the type would be text, data, or BSS, and then it would complain that this is already defined or used for a label. So this will be the last instruction for the text segment, and in this case the expression is just the value of this literal and can be of course encoded without generating new entries in the Fixup table. So this is actually now the complete text segment with incomplete instructions because they need to be fixed later. Now the next line changes the active segment to the data segment. So what happens internally is that now we have switched to the data segment, and now every byte that gets generated will go there. And bytes for the data segment will be generated from this .string directive in the next line. But here in general, it's important to know that first the symbol table gets updated for this definition of a label. That means in this case, no new entry gets generated here because we already have an entry for MSG, but its type gets changed to D for data because it's an address in the data segment. This is the active segment now, and its value will be the number of bytes generated there. So unfortunately here you do not see an effect that this value changes, but if we would have already generated some bytes here, the value would be whatever you see here. So this happens first, and after that the bytes for this zero terminated strings are generated. So after that we come to the second last line, which contains this EQ directive, and this will just change the type of this address symbol in the syntop to absolute because that's the type for integer literal. So you will see that this changes to A and the value to 1. And also in the last line we have an EQ directive, and this will change the type of CH to also A for absolute and the value to 2. And this was the so-called first pass of the assembler, where every line was processed once from the first line to the last line. And now you have to know that the first assemblers were so-called single-pass assemblers. Nowadays we are using multi-pass assemblers. The ULM is a two-pass assembler, but this two-pass or multi-pass assemblers still behave like the old single-pass assemblers. Now, what does single-pass assembler mean? Because memory was a limiting factor in the old days, you couldn't memorize the complete text segment and data segment that was assembled in this first pass. You immediately had to write to a file bytes that were generated for either of these segments. And you also had to write out in the end the symbol table and the fixup table that was generated in this first pass. So single pass doesn't mean that everything is done in one pass. It means that things are just processed line by line and just one thing gets done in this pass. And then in the second pass, this files generated from the first pass would be used as input. And then in the second pass, the text segment and the data segment would be fixed using this fixup table and symbol table. And this is what now the ULM assembler is doing in memory. So it will not generate intermediate files and then read them again. So it requires more memory compared to this single pass assemblers, but it's faster, it's more runtime efficient. So in the second pass, the ULM assembler behaves as if it would have read in this symbol table and fixup table from a file and also the segments, except that it already has this in memory already for speed up reasons. And now it applies patches to the segments. And for applying a patch, it uses the entries in a fixup table. It begins, for example, with the first entry here. Actually, the order is not relevant. And then it knows where to fix something. These 2 bytes here first, and how to fix it. It needs the value for the simple message from the symbol table. You see that here all the entries have a type different from unresolved. So in the end, we will have an executable. So it will use this value stored here, 32 in decimal, and then knows how to fix it. It needs to patch 2 bytes with the absolute value found here in the table. So it will change this here to hex 0020. Done. And then it will use the next entry in the fixup table to fix the next byte, in this case this byte here, with hex 01, and so on. Now you will see for a jump instruction, the second pass has to do basically the same computation as before. For computing a relative jump, it needs to subtract the address of the destination, determined by the value of this halt symbol, which is an address in a text segment with value 28. From that, it needs to subtract the address of the current instruction from where you want to perform the jump. And in this case, this gives 16. Then you apply this right shift by 2, which will then be 4. And then you will see that these 3 bytes here will be patched like that, where you have here hex 04. And that's basically it. So in this second pass, here we get an executable. That means now we have a patched text segment. The data segment was not changed. And this now will be written to a file, to a.out file, which will be executable on ULM. Of course, with just one example, not everything can be explained about assemblers, how they work and what you can do with them, but it's a good starting point to understand more about them. And of course, on the website, you will find additional information and also examples like the code here. And in this code, you see that in this EQ directive, we have an expression where we compute the difference of two labels. And now you already know the syntactical rules, and syntactically, such an expression is allowed. But in addition to this grammar rules, you also have semantic rules. And not everything that is allowed by the grammar is semantically allowed. In this case, this is actually the case because one rule states that if you have a difference of two addresses in a data segment, the expression has the type absolute. And of course, this makes sense because you are computing the number of bytes between two addresses in the same segment. And here, the purpose is also kind of clear. You can use it to count the number of bytes used by the assembler for generating the string, including the 0 byte. So with that, you cannot forget to also count the 0 byte. You will also see that there is a rule that address in a data segment plus an absolute value is also an address in a data segment. So this also would be allowed to add to a label an absolute value. What is not allowed is to add two labels, because this would be an illegal type and you would get an error message. And this error would not be caused because you violated the grammar. It is caused by violating these semantical rules. On the website, you will also find information about other directives for generating data, like a single byte or a word, 2 bytes, and how the assembler is taking care of alignment restrictions. And in the example here, you will see maybe that the symbol table contains in the end some values that you might not have expected. But let's review how the assembler is processing this source code line by line and how it actually is filling the symbol table and generating data. And then it actually will become clear what is going on. In the first line, we just have this .data directive, so we switch to the data segment, no big deal. And now in the second line, we have a directive for generating a single byte, but we also have a label. Now first, a label generates a new entry in the symbol table. In this case, the type will be D and the value 0, because 0 bytes were so far generated for this data segment. And that's it. Then some byte gets generated, and we proceed with the third line. Here again, we have a directive for generating this time a word, 2 bytes, which need to be aligned to an address which is a multiple of 2. But before that happens, before this data gets generated, the symbol table gets a new entry, and in this case again, type D and value 1, because so far just 1 byte was generated. And then the word gets generated. However, the assembler knows that a word needs to be aligned to an address which is a multiple of 2, and because currently we are at address 1, it will insert a padding byte. So it will advance this counter first by 1 and then create 2 bytes with this value hex for 2, 0 extended. And that means in the symbol table, this symbol W, which probably should point to this word, actually has address 1 in the data segment, but this word is stored at address 2 in the data segment. And that's probably not what you wanted. To overcome this problem, you can use the .align directive, which I inserted now here. And you see, before we just generate again a byte with label B. And after that, this .align directive tells the assembler to align the data segment to a multiple of 2. And it will, in this case, do that by inserting this padding byte as before. But that means that after this directive is used by the assembler, the counter for the data segment has value 2. That means if we now process the next line, the value for this label used in this directory is now 2 in the data segment. And that means after that, we again produce the bytes for this word as before, but now this entry in the symbol table actually points to this word. In the example, I mentioned the BSS segment, also in many videos before, but you haven't seen so far examples for it. On the website you will, and also here, you see that the BSS segment can be used in your assembly code like the text or data segment, except that it's only allowed to generate their 0 bytes. But you can otherwise use the same directives as in the other segments. So for generating a 0 byte, you can use the .byte directive, but you have to specify the value as 0. This is inconvenient for generating, let's say, 23 bytes. Here I'm doing that with the .space directive, which you also could use in a .text or .data segment, but here it's most important to have such a directive. And here I'm also, by the way, using the strict to mark the start of this region in memory and the end with some labels, so that I have a pointer to the buffer, a 0 initialized buffer, and a pointer to the end. You will also see when you look at the assembler output that actually no data gets generated for the BSS segment, because we know the data would be a list of 0 bytes, a sequence of 0 bytes. So the assembler is just keeping track of how many bytes are required for the BSS segment and what is the alignment restriction. Of course, you also can use the .align directive as in the data segment. For the implementation of the ULM assembler, I often looked at the GNU assembler on my platform, how it supports certain features of an assembler, and I also took a few bad things. That, for example, this .eq directive doesn't mean that a symbol is equivalent once and for all to a certain value. You can change the value of a symbol defined with .eq. And this happens here in this example. And with this example, I want to finish this video with some food for thoughts. What would you expect does the data segment look like after the assembler generates code? Of course, you can try it out, but also try to understand that this is consistent with how I explained the code generation for the ULM assembler.